why we do what we do on everyday life. I think that we all share, I mean, it doesn't matter if it's a theorist or an experimentalist, is the fact that what makes us in common is the fact that we love and we admire the beauty of nature around us. And we are bold enough that we ask questions about how our universe works. So we ask what we think are, in any given moment, fundamental questions. So questions that really go to the point, and maybe sometimes in a level higher and higher with respect to what our knowledge is in a given time, in the inner workings of our universe. So, you know, we start when, if you think physicists, Alan Newton, of course, or Galileo before him, we ask questions like, you know, why do bodies fall? And then we move to questions that might be even trickier, or maybe sometimes are simpler. Sometimes they reveal some very deep reason. So why does the moon always show us the same face? And in the beginning, right, you know, students answer saying, well, because it has the same speed of rotation under, you know, around itself on the Earth, and then in the end they end up watching us a long time. Speed of revolution around the speed of rotation around Earth. But of course, the answer is slightly different from that. We have to think a bit better. And what is the cause of that? And then we go to questions which actually demand some more understanding of what is the physics behind, right? This is shown also in this picture. One of the questions that we ask since we are kids, right, is why the sky is blue. And in fact, there is not such a very easy answer to that, right? You have somewhat to know some physics to be able to answer this question. And then when you go in school, I mean, in university the first 3 years, and you start understanding the Maxwell equations, you realize that there is something kind of useful, right, in the way that we think as a physicist. We think about scales. What is the scale that matter? And of course, you know, at this length and this wavelength for the light, what matters is really the atom, right? That is as a whole, but only if the atom is neutral. So if you can actually resolve what's happening inside the atom, right? So the atom then is not neutral anymore. We somewhat seeing what is inside and those wavelengths. And we have basically two charges which are roughly in the distance of the radius of the atom. And then by a very simple computation, which you can do also by analysis, dimensional analysis, you realize that the probability of scattering of light depends on the wave of the frequency to the fourth power. So it means that light, which has a high frequency, scatters more than light which has a wavelength which is longer. So blue scatters more than red. And by just using dimensional analysis, actually, you can try to explain, you can explain why if you look far off axis with respect to the sun, the light looks like blue, because the blue scattered more than red. So a question for you now is why the sky is red during sunset. So I'll leave this for your consideration. Then, of course, once we get successful in trying to answer questions, we take on or more difficult ones, right? We feel confident and we ask more, even more fundamental, right? So what are the constituents of matter? How do they interact? What is the origin of the universe where we live? Why the universe looks very symmetric or very asymmetric? The way we look at it now, it was always like that before. The symmetry of the universe depends on the energy scale where we are looking at. or is a fundamental property that is invariant under any scale, depending on, is independent in the energy at which we are looking at. So the other thing is becomes even more challenging, right? Is the physics that we measure or we know now, was it the same at the beginning of the universe or billions of years ago? Will it be the same in the future? Well, all these questions are very exciting, and that's how both experimentalists and theorists work together to try to understand them. Right? So how we do this? Well, we have experiments, we have accelerators. For example, we have a wealth of experiments. Some of them are more observational, so that we look or we measure things that happen independently on us watching them, or not watching, but measuring them or not, like in astrophysics or astroparticle physics, where we don't control the source, let's say, or we build experiments where we do control what is happening because it's ourselves that produce the high energy initial particles. So that's what we do, for example, in accelerator experiments. And it is shown here is an image of CERN, of the area around CERN. This is not reality, right? There is this symbol which is drawn by me, let's say, and represent the accelerator which is underground, which is a 27-kilometer accelerator, which is now called tunnel, which is called LHC, Large Hadron Collider, where we scatter, right? We smash protons, and we see the results. We look at the results in big detectors. So you might have seen this movie many times. Here in the wall, you have seen very briefly the Lagrangian standard model, which we see again soon. So this is a famous animation that all of us have seen maybe many times. So this is a proton with quarks going inside it that scatter, right? You see they collide head-on with another proton, and we record the outcome of this collision in a big camera, which is called detector, where the tracks of the outgoing particles can be made visible. We can reconstruct them. This is, of course, an animation, but we can doing backward engineering, what we can tell what happened in the very short distances. In this case, there are two leptons, a muon and an anti-muon, coming up, presumably from a Z-boson decay. So this is a pictorial view, an animation of what's going on in the scale of human size scales. Of course, we can also try to see what happened at the very small scales, and scales at the Fermi scale, and even shorter, up to the 10 to the minus 13 meters. This now is an animation based on a simulation tool that all of us know in the field. It's called Pythia, where events are really described as they happen from fundamental Lagrangian of the standard model, right? So it's an animation which is based on a realistic simulation of an event, which describes a top anti-top production. Top is one of the fermion in the standard model, the heaviest fermion in the standard model, and several of us are fond of. So this is a UU bar annihilation into a TT bar pair, which immediately decays into WB. You see this animation, they also decay and they form a cascade of particles, which then leave a track in the detector, which is in this animation very, very far away. This is something that happens on the scales of 10 to the minus 22 meters. Okay, so something which is inside the vacuum pipe where particles run in very, very small scales. And what we see after, we don't see anything that is happening now. We see much at later time. We see these hadrons passing through the detector much later time. So this is what a theorist does. He tries to reproduce what is seen in the experiment from a fundamental point of view. So how do we do this? Well, we use a Lagrangian. We use really a Lagrangian that we learn in school to actually predict what can be produced on a probabilistic way following quantum mechanics in the final state. So how do theory works? Well, it works in two ways, right? There are two directions that theory works in this circle of knowledge, right? There is a top-down and a bottom-up direction. There is a top-down when you think of a theorist like in his office or her office, thinking about new theory, making prediction, then giving this prediction to fellow experimentalists that are going to take them and compare with data. And then by learning if this prediction agree or not with data, you go back in this arch of knowledge to revising, right, your hypothesis. So it's a bit a Bayesian way of learning, right? So they imagine, create models, they draw prediction from them, and then they infer from data how to modify their assumption. So in order to do this, after many years of technology, which has been introduced by Feynman many years ago now, we developed a technology to actually make this computation as accurate as possible to compare with data. Of course, this has become an activity on its own, and sometimes it's difficult for theorists to explain what they're doing because it becomes so technical and so involved that it becomes very often a very tight community of experts. So it becomes like a bit like in sports when you only are an expert of curling, for example, then you can discuss with other people who love curling very much all the subtleties and the pleasure of the sport. This becomes a bit also sometimes for theorists and experimentalists alike. So theoretical physicists are famous in the community of high energy because they follow a career, which is now the most common for everybody, in fact. But in the past, it was more common for theorists than for experimentalists. So they have a long training, right? They go around, they change groups, they go abroad, and they settle after some time, and they build their own group after long training. So it's a bit like artists were doing in the 19th century or even before, even 15th century actually, where they were traveling, learning new techniques, having inspirations, and coming them back to paint a new theory somewhere. So Raffaello did this, for example, and many philosophers did the same. So this is a build, a path towards independence that characterize all scientists, basically, but even more high energy physics, because high energy physics is really an activity which is worldwide, right? So we don't do experiments in our lab only, like, at home, but we also do experiments which are worldwide. So it's a worldwide community. It's normal for all of us to be in a conference call with, China and the US and in the same moment, right, in different parts of the world. So what is our current understanding? Well, what we have now is a theory. It's called standard model. We'll talk very briefly about it. But we have a theory that somewhat describes nature up to a given scale, up to an energy scale of, like, say, 1 TeV, right? 1 tera electron-volt, 10 to the 12 electron-volts. And beyond that, we know somewhat for several reasons that might not be the whole story. And what we're trying to do is to devise, right, a path which goes beyond what we know and adds to it and completes it. So what do we have? We have the standard model. So you see that you might see in this t-shirt when the standard model is summarized. There is a very simple description of standard model in a one-line formula. It's so simple, in fact, that now, theorists like to think about standard model as a sphere, right? In the sense that it is a very simple theoretical object, which is composed by matter and interactions and is ruled by gauge symmetry. Very simple, very successful, and somewhat too simple to be the whole story, if you want. So the way we like to think it is that this sphere actually might be if looked more carefully, closer, might be leading, right, might be looking like some beast, which we don't know yet what it is, but whose details we have not resolved. So maybe, the standard model is not a sphere, it's just a sphere because we are looking at it from very far, from very low energy. But if you go closer to it, if you go higher energy, we will start seeing some details, some horns or some ears. And then we can even closer, we could distinguish if it's a dinosaur or a simple cow. That's what we are doing nowadays. We are working with the theories which are in the intermediate step between full-fledged UV theory and something which goes in the direction of standard model, and we call them effective field theories. And that's what several of us, anyway, one way or the other, are working with. So how will a theorist, a phenomenologist, someone who is more interested in the theory aspects of particle physics, can develop a career within the IMAPP? Well, we kept an eye on this in developing the course. I mean, Kevin will talk more extensively about that, so let me only mention that there is a path, actually a special eye that is being given towards theory from the beginning, which is not always the case in our local courses in our universities, where at each semester there will always be at least one course which is a theoretical oriented one. This allows to have a preparation in theory which really is enough to understand and to even work on Pheno aspects of standard model and physics beyond, more from an angle which is more of theoretical nature. So this is my last slide. So I concluded. So we can study nature in various different ways, right? We have colliders, we have gravitational waves, we have observation through satellites, we have cosmic ray experiments on Earth. You can choose many different ways where particle physics always, one way or the other, are fundamentally intellectually important. What is your best bet? What will you choose as your path for maximal interest and minimal effort, if you want, and maximal gain? I leave it to you. Thank you.